Alright, so I've cleaned up the board. At this point, I'm going to recap the statement of the Kotzig-Ringel-Rosa conjecture, work through an example, and prove our main theorem for today. So, the Kotzig-Ringel-Rosa conjecture asserts that for all functions f in Zn cross Zn, and Zn to the power Zn, so for all functions in this set, subject to the image of the domain having size 1. Another way of stating this condition is that if you compose the function with itself n minus 1 time, the function you get is an identically constant function on the domain. Alright, now the Kotzig-Ringel-Rosa conjecture asserts that for every function subject to this condition, we have, and I'm going to rewrite the condition this way, that the maximum over every permutation sigma in the symmetric group of the following absolute difference, and here now I'm putting the inverse just to emphasize that we're relabeling the function. Alright, so the conjecture asserts that for every f subject to this fixed point condition, we have that the maximum over all permutations sigma of sigma f sigma inverse of I minus I, this is the edge difference, is equal to n. Okay, and I want to illustrate this with the example that we saw. So let's give an illustration. So take the function gf to be the one we started up with, self loop at 0, 1, 2, and let's say 3. So the vertex set of this graph is 0, 1, 2, 3, which is basically Z4. Okay. Now, I want to show you that there's a permutation that I can apply to the graph. I can relabel the vertices such that this condition holds. So let's look at the permutation. So take sigma in S4 to B. And I'm going to write the permutation in Cauchy notation. So I'm going to say 0, vertex 0 is going to be changed to a new vertex. Vertex 1 is going to be changed to a new vertex. Vertex 2 is going to be changed to a new vertex. And vertex 3 is going to be changed to a new vertex. Okay. So I'm going to choose to maintain 0 at 0. I'm going to choose to swap a 1 and 3. So 1 is going to be replaced by 3. I'm going to choose to put 2 at 1. Yes, I'm going to replace 2 by 1. And at this point, I have no choice. 3 is going to be replaced by 2. So once I've specified how the permutation works, let's apply it to the graph to see what happens. So by applying sigma to GF, we obtain the graph that we're going to call sigma applied to F sigma inverse. This is the new graph that we're going to obtain, given by. So let me describe how the permutation is going to work. So we start with the following graph. So GF initially was the graph where 0, there's a self-loop at 0. There's an edge going from 1 to 0. There's an edge going from 2 to 1. There's an edge going from 3 to 2. Okay, so this is the original GF. And then the new graph that we're going to obtain is GF sigma inverse. Okay? And this graph is the graph I'm going to obtain when I apply this permutation sigma to the vertices of my graph. Okay, so if I apply the permutation, it says wherever I have 0 is going to remain 0. So this vertex is going to remain 0. Wherever I had a 1 I'm going to change it into a 3. So this vertex is now going to become a 3. Wherever I had a 2, I'm going to put a 1. So this vertex is now going to be a 1. Wherever I had a 3, I'm going to change it into a 2. This vertex is now going to be 2. Okay, so now, how do we check that the condition that we want holds on this graph? To check that the condition that we want holds, what we compute is the absolute difference along every edge. So I'm going to take the first edge here, the self-loop, and this self-loop edge spans the vertex 0 to 0, so if I compute the absolute difference of 0 minus 0, I get 0. So I'm going to put it in a square bracket, the edge label, so this is 0. If I compute absolute value of 0 minus 0, I get 0. If I compute the absolute value of 3 minus 0, I get 3. So here I put in the square 3. If I compute the absolute value of 3 minus 1, I get 2. So I'm going to put in here absolute value 2. If I compute the absolute value of 2 minus 1, I get 1. So I'm going to put here absolute value 1. Alright. Just to emphasize that this is a 1. Okay, so as a result, I get that we see that the number of different integers in these squares is indeed equal to 4, and that's exactly what our optimization function is trying to solve. We are trying to find a sigma such as this one, which basically maximizes the number of distinct integers in these squares. And the numbers that I put in the squares are absolute values of differences along every edge. Note that if I had computed the absolute difference along every edge here, the set has size 2 because this guy would have edge weight 0, so let's actually write it. In the square here, I would have a 0. Here, I would have a 1. Here, I would have a 1 again. Here, I would have a 1 again. This is sort of the worst possible case because the number of distinct integers in the square is 2, whereas here, the number of distinct integers in the squares is as large as possible. It's actually 4. Okay. So the real goal of the conjecture is to take a function and basically try to relabel the vertices of the function so as to maximize the number of distinct integers in the square. Okay, so let's prove our main theorem and then discuss the application of this conjecture. So proof, theorem. The graph GF of f, a function that outputs numbers in Zn and takes as input numbers in Zn. All right, a function GF is such that such that the maximum over sigma in Sn has size Alright, so let me write here in Zn. Zn is equal to n if and only if and only if f if and only if there exists sigma gamma in Sn and S in -1, 0, 1 Zn. So this is S is a sine function which takes inputs numbers in Zn and outputs either -1, 0, or 1 such that f of I is equal to sigma, let me write sigma inverse of sigma of I plus S of sigma I times gamma of sigma of I for all I. Alright, so basically, if you give me any function and it's a solution to our optimization problem, then there must be permutation sigma and gamma, which basically additively express f. You can think about this as a sum of this permutation. And here, what I really mean is gamma of sigma of I. Okay, all right. So let's actually prove this statement. Okay, so the proof is relatively straightforward. So let's prove this, and then we'll discuss some of the application. All right. Now, we're going to prove the hardest direction. The easy direction follows immediately. The hard direction is to actually understand why is it that if you have a solution f to this optimization problem, this expression follows. To go in the other direction is relatively straightforward. In the interest of time, let's just prove the hard direction. So assume, so here we're going to assume that the maximum over sigma in Sn of the size of this set, sigma f, sigma inverse of I minus I, okay, for I in Zn, this is a set. Assume that this is equal to f. I'm going to make this assumption. That's a hard direction. Okay, so if we make this assumption, we assume that this f is actually a solution to our optimization problem, then, let me write it here, then something interesting happens. Then there exists gamma in Sn such that the absolute value of sigma f, sigma inverse of I minus I is equal to gamma of I for all I in Zn. So if indeed it is true that you take the absolute value of all the edge labels and you have a set of size n, because we're computing the difference of integers which range from 0 to n minus 1, the only way that you can end up with integers with a set of size n is if all integers between 0 and n minus 1 occur. Now, if every integer between 0 and n minus 1 occur, this really means that we're looking at a permutation. The absolute value of the difference is a permutation of integers between 0, 1, 0 up to n minus 1, and gamma denotes that permutation. Okay. But once you have the permutation, you're basically done. This now implies I now basically have this absolute value expression that I can remove. So I can remove the absolute value. It follows, therefore, that sigma f sigma inverse of I is equal to I. So let me do it one step at a time. So sigma minus I is equal to a sine function of I times gamma of I. And this is the sine function we were talking about here. Because when I remove the absolute value, it can be plus or minus, I have to account for this sine function. Okay, but then we have a home run. I can do a change of variable, move the I on the other side, and basically get our desired result. So from this expression here, I can write that f of I is going to be equal to sigma inverse of sigma of I plus s of sigma of I times gamma sigma of I, and close for all I. Okay, and this is basically what we wanted to show. This expression here is basically what we wanted to prove. And we've indeed proved it. Okay. Going in the other direction is really trivial, so I won't really mention it. Okay, now why would you care about this problem? It turns out that this Kotzig-Ringel-Rosa conjecture was brought about because it algorithmically enables us to partition the complete graph into disjoint copies of a graph which satisfies our condition. What this means is that if you give me a complete graph, and a complete graph is a graph where every two vertices are connected by an edge, are adjacent, you can split the complete graph as a cake into edge disjoint copies of some other smaller or larger graph. In particular, what the Kotzig-Ringel-Rosa conjecture does, it gives us an algorithm for basically cutting a complete graph on 2n-1 vertices into 2n-1 copies of gf, which is a function from zn to zn. Okay. So that was the original motivation for the Kotzig-Ringel-Rosa conjecture, and I really like this problem a lot because it brings together two perspectives on graphs. So if you ask somebody who did calculus what a graph is, he will describe the x-axis and the y-axis and draw points. Basically draw points on this graph and describe the graph of a function. What I really like about this problem is that it basically combines two ways of thinking about graphs. One way of thinking about graphs in combinatorics is vertices and edges, but you can think about these functions also as having graphs. So if I was to draw these functions here, for example, the gf, what would it look like? So the x-axis will have here 1, 2, and 3. The y-axis will also have here 1, 2, and 3. Here, of course, is the origin. And then you would actually plug these points. You would say 0, 0 corresponds to this guy. 1 goes to 0, so 1, 0, the x coordinate is 1, and y coordinate is 0, corresponds to this point here. And you would say that the edge 2, 1 corresponds to x coordinate 2, y coordinate 1. So you plot this. And finally, 3, 2 is x coordinate is 3, and y coordinate is 2. So 3 and 2, the point would be somewhere here. So what I really like about this problem is that you can actually combine these two ways of thinking about the graphs. And that way of thinking about graph is critical to actually basically addressing the conjecture. So if you're interested in this problem, I plan to post additional videos describing an approach to tackling the conjecture. But for an introductory talk, I think it's a good idea to stop here and answer other questions which came up for the talk. I want to point out that there's some non-trivial result which follows already from this theorem. This theorem buys us, for example, that you are not free to choose any permutation gamma. There are some constraints on the permutation gamma that you can choose. And we proved that the number of gamma that you can choose is basically bounded by n minus 1 over 2 factorial the whole thing squared. Okay. So just writing this basically allows you to count or give an upper bound to the number of graphs which already satisfy this condition. Okay. So as part of the talk, I was asked to basically give a few answers to questions about mathematics in general. I prepared a few questions that I'm going to answer. The first one was, what is it I love about math? I would say that what is unique to mathematics, which really drew me to it, is the ability that math has to formulate precise statements. It's very hard in life to find places where one can agree on what's being asked and find a definite answer to a question. And what I like about math is the fact that you can formulate very precise statements and agree on a proof that the claim was correct. And I find that in other disciplines it's not so easy to achieve this. So in this regard, I think of math as a supreme form of art, in the sense that it's art constrained by logic, and the statement that you formulate are very precise. Unfortunately, not everywhere can you achieve that level of precision, but it may be desirable that life isn't precise everywhere. Okay. The other question was, what was my favorite math topic as an undergrad? It was much harder to answer, but here's basically looking back what my favorite topic was. I really enjoyed analysis as an undergrad, and it was the Weistra style of analysis, the epsilon, delta, and the formalization of calculus. I was drawn to analysis because I really had a fascination for math history. So the two favorite topics which went hand in hand as an undergrad for me is learning about math history, the history of mathematics, which I recommend any undergrad or graduate student to take a look at. Studying the history of mathematics in parallel to studying mathematics helps you understand why the definitions that we've converged on occurred, what is the historical relevance of different ideas, so you actually get a feel for how mathematical results occur. So history of math and analysis were my favorite topic. However, moving on to grad school, my favorite topics changed, so be open for change when you move on to grad school. Okay, the next question was, how did I prepare for grad school? It's harder to describe. I don't think that there's a recipe for prepping for grad school that applies to everybody. In my case, I basically went to libraries and browsed a lot of math books. I asked advice from people who were faculty and graduate students. What is it that they would recommend? Most of them advised that I should prep for the qualifying exam as early as possible. I thought that was a great advice. And the way I did it is basically going into a library, picking some particular section and browsing math books. In the beginning, I couldn't really understand most of it. I was enjoying the pictures, but it allowed me to converge to the type of mathematical arguments I liked. So don't be discouraged by the fact that you don't understand what's being asked. You can be drawn to a topic by the cool pictures. Topology is great for that. But browse as many math books, find what you like, and go for that. One of the books that had a very big impression on me were Bell's Men of Mathematics, although some argue there are inaccuracies in the book. It's a great book for learning about history of math, at least introduction to the topic, and Proofs from the Book. Proofs from the Book is a wonderful book illustrating some classical proofs in math. Okay. What was the most challenging part of being a graduate student? For me, the most challenging part of being a graduate student was to be both a graduate student and a parent. I became a dad as a grad student. I found it hard to manage, but through the process, I actually learned to do mathematics basically all the time. I've learned to do math in very unusual circumstances, so I'm grateful for that in retrospect. I had to be much more mindful of how I was organizing my time, and as a result, I've learned to do math all the time, basically. Whenever you see me doing something, I'm doing mathematics. Whether I'm sitting in the bus, whether I'm having foods, or sometimes even when I'm doing dishes, have some way of thinking about doing some mathematics. Okay, the last question was, what advice would I give to somebody considering grad school or an undergrad? The most important thing for me when thinking about grad school or a skill that was very useful, I think that setting up mathematical experiments to test conjectures turned out to be extremely useful for me. So I would advise any graduate student to pick up symbolic skills for programming any symbolic algebra package. My favorite is Sage Math, but you can use any of the others available. And it proved a very useful skill to be able to quickly code up some conjecture you have, especially in combinatorics, to test whether what you think is true, and if the experiments turn out to validate what you conjectured, then you can start trying to prove it. So this was great for me because it allowed me to rule out many conjectures which I thought a priori would be true and turn out to be false. So my advice would be pick up some coding skills. It's going to help you a long way, and it's actually going to inform your thinking. All right, so that's pretty much it for the talk I wanted to give. I hope you enjoyed the presentation and the introduction to the Kotzig-Ringel-Rosa conjecture. And as I said, be on the lookout for additional videos which actually is going to describe this functional take on addressing the conjecture. Thank you, and I hope you be successful in your mathematical career. Bye.